I'm joking, I'm not. So today we're going to talk, I'm going to talk about the one last thing about calculating error in the system, and then we will start PID controller next week. So I give you some sort of introduction to PID control before spring break, and then you go forget everything, you come back, I have a review on Monday, then we start. Sounds good? So I kind of prime you before break, and then I review that. All right, that's the plan. So the last thing is, well, there are two things. The last thing is disturbance rejection, but before that, I wanted to solve this example. This is the kind of examples you might get in your exams, in your homework, or in real life, because these are the design problems. So you're supposed to design a controller. Now, a controller could be anything, right? So how many of you have heard of PID controllers? Okay, what are PID controllers? Can you tell me? Yes.
Proportional, integral, derivative.
Yes. So it's a 3-parameter controller. All right. Now, if you add like an amplifier to a system, the amplifier is kind of a controller. It does something, right? It amplifies. Can filter something or not, but the amplifier itself, has a gain that can attenuate a signal, right? So that is a controller. But the only thing it controls is it adds gain. So if you see a block that is just a gain, that's also a controller. So you are basically saying, hey, I have an input that when I apply to my system, it doesn't give me like enough voltage. So I'm going to attenuate the signal, add gain to it, like multiply by a number. So it is enough for my system. So I can see a result that is understandable for me, for example. All right. So if you see something like controller K over there, K is just a number, is still a controller. Because you get an error, for example, and you say, okay, I'm going to multiply by something. Now, it could be something K greater than 1 or K smaller than 1. Still is a gain. Now, in PID, the P part, the proportional, is this K. The proportional part is just a block that has just a fixed number, doesn't have to do anything with the error, is 1 to 1, is proportional to the amount of error that you get. Okay, it either like multiplies the error by something greater than 1 or less than 1. So when we see this K, still a controller and it's part of your PID controller, but it's just a proportional part of it. All right, so consider the following system. Determine the appropriate gain K so that the steady state error to a step input is minimized. All right, so first of all the error that we talked about, we put H equal to 1, right? And it was all unity feedback. So this is a non-unity. To find the error, you have to go back to that original equation we had. How do we find error? What do you do to find the error? Yes, the difference between input and output, R minus Y, right? So when we wrote R minus Y previously, if you remember, so we said that, well, R is R, and then we wrote the transfer function, right? Whatever it was, we put it here. I'm going to call it T. And then to make things simple, we said, okay, let's see, it's just unity feedback, right? So the equation was simpler, but the error itself is the same thing. Now here, H is not 0, and it's not 1 anymore. This is not a unity feedback. It's called non-unity feedback. It means that there is a sensor which has a block that in the feedback loop, which is here. So this is basically your H. This is G controller, and this is your G of the system. Now, you can use block reduction to find what the transfer function here is, right? Then Y to R is going to be that transfer function. Make sense? Yes? So let's do that. Write the transfer function. What is I over R? Find T, the transfer function. and try to find the error. And you find the steady state error. Can you solve this problem? So what does this problem say? Let me go back here. So we found the error, right? Do you remember the equation for steady state error, the actual big equation that you had to use? Since it's not unity feedback, you cannot use the table I gave you on Wednesday, right? Do you remember the equation for steady state error? If not, go back to the lecture that I first introduced it, write the steady state. So I think this is what I wrote, but usually you also see with lowercase ESS also. But find what was this equation, put the transfer function in there and see what should happen so that this ESS is minimized. I'm gonna put a black screen for a little bit. I need to find something. You have this in your lecture. The Zoom classroom is doing something. Oh. Can you see it now? Wrong solution. If you found the solution, raise your hand. I'll go there. If not, I'll write it in about a minute. Just want to make sure that. All right. So what was the equation for ESS? Did somebody find it? How to find the error, steady state error? It's like a final value theorem, yes. So limit of S. So E here is your transfer function, something that we want to find the final value. Then we send S to 0. What does this mean? We want to know what is our error when times goes to infinity, which is when S goes to 0. So don't forget this S behind the E or whatever function that you're trying to find its final value at time equal to infinity, right? So if we do that, here I call this T, so we have R minus T Now, this is T over R. Now, T itself is, sorry, Y is TR, right? So Y over R is this. If I call this function T, then output is T times R. I can write 1 minus T times R. So you can always say, if you had a non-unity feedback, your error is 1 minus the transfer function of your system times the input, right? If it was unity feedback, you have already done, you have a table, as soon as you see that, go to the table, find those errors. If it's not non-unity, you have to do all of them by hand. This is a good shortcut, 1 minus T times R. Now, if we put this here, limit of S, 1 minus T times R when S goes to 0, what is our R? What's the input here? Michael, what's the input? Step function, yes, is 1 over S, right? Or A over S, whatever you want to choose. I'm just going to say is unit step. Because it didn't say is a unit step, but I'm just going to assume is unit step. So I'm going to say here, from this information, I know R is 1 over S is a unit step. So if you replace that, your ESS is going to be the limit of S, 1 minus T times 1 over S, then S goes to 0. I can cancel these two out, right? So what I get is 1 is a fixed number, T is my transfer function that has S in it, right? So basically the solution is 1 minus T0, agreed? So TS, I'm going to write TS so you know what that 0 came from. Because T of S is my transfer function, T of S. So it's basically this guy. Now, I'm going to write it, so if you don't have that. So 1 minus, if you plug those values, you will get 4K over 8 plus 2K. Now, what should we do for this to be minimized? Go to 1, right? Because then is 1 minus 1 equal to 0. The minimum value of the error we want is 0, right? That's what we would like to do. So we want, so since we want ESS equal to 0, so ESS, same thing, just write it lowercase. Then 4K over 8 plus 2K has to be 1. This gives K to be 4. So what does that mean? So identify where K is. K is right here. What is K? It's a controller gain, right? So what did you do here in this example? Can someone tell me? So you adjusted the gain of your controller to get a gain, a steady state of 0, right? So this is a control, this is the control decision. You made a decision. You knew that this is my system. I'm going to see for a step input how this system behaves. Now, if we plot this in MATLAB, you're going to do that. If we plot this in MATLAB, if we give K 1, we would expect to see a steady state error, right? Then we would change K to 4. It has to give us a steady state of 0, correct? Now, this is not the only thing you would do when you're designing a controller, but it's part of it. So usually when you're designing a controller, you're trying to meet some specification. Usually time of like the peak time or settling time, those are very important as well. So you don't usually have only one requirement. So steady state B0 is not your only requirement. Why is that a bad thing if it was the only requirement you had? What would happen to your system? What what does your system look like or could look like if you only had one requirement and that's the steady state error to be 0? Yes.
You could, like oscillate really violently for a really long time and then eventually get to.
Because this is at time equal to infinity, right? So it means that when a steady state is 0 is that at time equal to infinity, my system eventually will track my input. There will be no error. It exactly goes where I want. You're driving a car. Sorry, Zoom classroom, you can't see me. It's really cool right now here. Okay. So like me driving my car, I have to 5 minutes time on the road. Right? You don't want that, but if you close your eyes in 5 minutes, you open your eyes like, yes, you really want it. So that would make a bad controller. You met the specification, but that was not enough. So usually that's not your only requirement. You usually have some other requirement, such as person overshoot less than this. Settling time, the time that you will get to that steady state 0, 2% above or below is going to be a specific time. Then when you have 2 or 3, then your controller would make sense. It would be a proper control design, okay? But this is always a very good insight when you're designing your controller, because you always want to be very close to what you want to track. If you're going to be 25 miles per hour, you want to make sure you are close to 25 miles per hour, right? Or there will be consequences. Make sense? So, because we already tried person overshoot and like rise time, we never actually use a steady state. So this is just a complementary to what you knew before. Now, on your MATLAB, write the code. This is your system. See the step response for different values of case. You can create a vector 1, 2, 3, 4, or you could change the vector value of k 1, then 2, then 3, then 4, plot all of them and see the response of your system. All right. I'll walk around. If you are here, if you are on Zoom, once you have at least 4 2Ks, 1 4, 1 something that's not 4, post it on Discord so we can check over there. Sounds good? You could use any, so I'm going to write the final transfer function for you here, so it just kind of help you in coding. So your T is going to be K S plus 4 over S plus 2, S plus 4 plus 2K. So that's your T of S. You could use this directly. Because that's what we usually do. We can use our, like on paper, we can find a transfer function and code it, or you could simplify this in your MATLAB code. Either way it works. All right. So it's 3:24. I think I check on you in 5 minutes to see where you are. once you've done that, I want to be able to look at your plot and understand when you have the steady state error and then you don't have this. I can also type things here. Best way is I'm going to ask one of you that submitted, and I'm going to show that. Zoom Classroom, hopefully you are also working. Just submit on Discord. Let me go to Discord. Let's see. That you have, do you both of them? I mean, at least one play 4 and one on 4. For someone that has 4K, both 4 and K is not 4. Submit in Carmen, submit on Discord or here. Oh, you're not here. Submit. And then you don't. Did someone put on Discord? Looks like I hear Discord. Okay, nice. I love it. Okay, let's talk about that. I actually have to go to Zoom and share a different screen. Okay, Zoom Classroom, do you see a plot of colorful things? I think that was a yes. Yes, okay, so this is how steady state error works. So now for K that was equal to 1, it went, the final value was 0.4. We were tracking a step function, right? What's the maximum value of a step function when it was 1 over S in time domain? 1, right? Because R of t, step function in time domain is 1t, 1 for all times, right? Now, if you have AT is like 2, 3, 4, 5. So the magnitude or the DC gain can vary. But here, because I use 1 over S, so the final value is 1. Now, the error, the steady state error is the final value of your function, of your system with respect to 1, which means that your system should track and reach to 1. Now, when k was 1 is 0.4, so the steady state error is this much, between 1 to 0.4. Output minus input, input minus output. Your input is 1, your output is 0.4. So there is a steady state error between them. So why do we care about the steady state error? Because in the transient time, the system is working toward reaching the final value. But in a steady state, it's already did. It's not going to change anymore. That's where we measure the difference. Now, if k is 2, now the difference, the steady state error is, let's say, 6.68 to 1. Then here is close is 0.8 to 1. At k equal to 4, the system finally reaches to 1, which we expected because we designed the controller for k equal to 4 to be a steady state of 0, right? Now, if you give a bigger k, you're now going to have error, still steady state, but over. So you're overshooting it here, right? Now, so you could use theory, the equation, to find the controller parameters, or if you were here and you said that, okay, let's say the k was 1. What does it mean? There was no controller, right? If k is 1, the block would be 1, become the signal. So there was no controller. It was still a feedback, but there was no controller design. In that case, k is 1, right? So the blue system is your system without controller. Your job is to find a k that fixes the system. Now, for input of step input, your system had 0.6 a steady state error. So one of the things you should do is to eliminate this. That is possible used by adding the gain. That's where the proportional part of PID control comes in handy. Brings everything up or down across the whole time domain. Make sense? All right. So now we'll see in the case of this purple k equal to 4, you see that this is happening around 1.5 seconds. Now, depending on your system, this might be too slow, right? So you will go and check your other requirement that, hey, what should be the settling time? Because that's the settling time, right? It might be your settling time should be 0.5, for example. Then do you remember what should you do to shift this to the left? Can someone remember? Just tell me, what do we have to do? Don't have to tell me exactly. So we want to change the settling time, make it faster. Do you remember how we would make our system faster? We worked on this, if you remember. What would be one way to do it? You remember we had S-plane, and then I identified omega, D, and sigma, and then I showed you those lines. So adding a pole to your system could do it. Remember, one of them was maybe put a pole or shift the pole of the system farther from the line. So that's how you design controller. You look at the response of your system and think, what do I need to do? Now, okay, I need to make the system faster. What are the tools I have? One is maybe add a pole or shift the current pole of the system slightly forward or backward. All right, that's what controlling is. Like, you have so far all the knowledge you need to design a controller. From here, we will basically learn different kind of controllers and what they do. But the knowledge is done. Like, you learned everything that you need so far. Well, except that last thing that I'm going to tell you, but it doesn't have to do anything with controller. It's just more of the noise. Good job. All right. Let's go back to my iPad. Oh, thank you, Brett. Best TA. I don't want you to graduate. I can't mess up with that. Haha. He put me on his committee. Shh, naive. No, like Brett has been a very good TA. Even though he's a grade, he gets paid as a grader, he worked as a TA, which is amazing. But I can't pay him more, so But I'm a cool boss, so. All right, yeah, enough about me. Okay, so the last thing you need to know, and then you're able to basically design any controllers, is how do we include the impact of disturbance in our system? Do you remember we have two kinds of disturbances when they can show up? What are they? Who do I want to? Oh, let's look at Zoom Classroom, right? Kyle. Kyle H. Do you remember what are the disturbances? Kyle H, can you hear me? Large, oh, that was, I don't know if you can hear me. Okay, anybody here? What kind of noises we had in our system? Alexis. You can't tell me one of them, Sam will tell me the other one. Mm-hmm. So, yeah. Thank you, Kevin. You saved her on time. James, tell me the other one. Huh? Damping is not a noise or disturbance. It's something that is characteristics of your system. So noise, it's not because of your system. It's because of something else. One could be process noise or noise from the environment, right? It's because your system is an environment, any environment, you could have noise. What's the other one? Sensor, right? So we call it measurement noise. So that comes in place when you have a sensor, because we don't have 100% ideal sensor, which are the same thing, 100% ideal. We don't have ideal sensor. If we had, we just put unity feedback. But in reality, we're going to have a transfer function for them, right? So how do we analyze a system if we have those noises? Because every time you calculate error, there was just input and output, right? And then if there was disturbance, I said, assume disturbance is 0. Now, what if the disturbance is not 0? What do we do? So do you remember these systems are LTI, right? So we could say that, hey, for a system that has disturbance and input, basically you have two input, right? How about we look at the behavior when we only have the actual input, then we only look at the system when we only have the disturbance as input. And then combination of these two are going to be the response, because we can use superposition in an LTI system, right? So what does that mean? Let's say you have a transfer system with the GC as your controller. Then this is where, this is G, the plant. This is usually where, say W is your noise, WS. This comes in and usually could be plus, minus, really depend on what kind it is. This is your R of S, which is your reference. And then this is your feedback loop, negative. Let's say you have H because let's say we have an actual sensor here, right? So let's say this was the case. Now, how many inputs do we have here to the system? 2, right? R is an input, W is an input. As an input we don't want, but we have it, right? Now, when we are solving these kind of problems, we want to know how well our system rejects the disturbance, right? So when you design a controller, you're basically saying, okay, I'm gonna have some vibration here. I'm gonna reject that. I'm gonna design my system such that if there was vibration to this magnitude or frequency, the system is gonna reject it. Basically, it's gonna damp it. So I'm gonna probably add the damping of my system, right? So to see the effect of that disturbance, you can say, let's put my actual R equal to 0, the input. Let's assume this R of S is 0. So before this is 0, the error is here, right? Your actual input, then your output, you see the difference, that's your error, and then you're controlling the system, correct? Now, when we are trying to see what is the system response to disturbance, we are going to say that assume this guy is a 0. So we don't have an input. What's the only input that the system has right now? Your disturbance, right? Now we're going to say, let's see the behavior of the system if the disturbance was the only input. And how do we do that? You say, let's say it was a step, right? Step function, because we know how step function look like. So we set that omega s to be 1 over s. Now this is our new system. So if you can rotate it kind of, so I'm going to show it here. So now, well, this is going to be omega 1 over s. Then this is g, this is y, and I have h and gc here in my feedback loop. So I just kind of rotated my system, right? Now the system has one input, one output, and I'm going to see what's the response of my system to a step input. Now, for your system to reject the disturbance, what kind of a steady state error do you expect to see? 0, right? Because if your system can reject all of the disturbance, there will be no error. The response of the system would be exactly where the disturbance is. So if your system did that, it means that it can eliminate the effect of the disturbance to your system. So this is how you will see the response of your system to disturbance. Then we will call this disturbance rejection. Like how well your system rejects the disturbance, and it's when ESS equal to 0. Sometime, or most of the time, the system itself might not be. You have to design your control in a way that it will do it. So you will have to adjust the controller to bring that ESS equal to 0. Once we've done that, we could also, yes. No, so here you see what is here. So if you have plus, it's like positive feedback here right now. If it was negative, it's a negative feedback. We don't change the system. Yeah. So this is a -1 block here. So that's like a signal, right? You make sure that your system is the same system. So I kind of rotated it so for you to see why there is one input, but you don't actually do that. I'm gonna tell you how you write the whole transfer function, and then you just make one part of it 0. So you don't use this to create your system. This is just a visual way to understand how your disturbance is your input. I basically rotated my system, all right? Now, if you were using, so you say, okay, I know what disturbance does to my system. You want to know what the input does to your system. That's called tracking. That's the same thing we have been doing so far. You put your disturbance equal to 0 and see what's the response of your system to a case that there was no disturbance, right? So when you find both of them, you can look at both of them and then change your controller to bring the impact of disturbance down and follow your input well, right? So designing a controller is not like, okay, I'm going to change one thing, everything going to be strawberries and rainbows. Rainbows and what? Not strawberries. Flowers, butterfly, whatever. Yes. Sweet things. It's never going to be like that. You always have to compromise and find a midline that, hey, I'm designing this controller because sometimes you have two requirements that don't align. You have to find a middle ground for it to control your system, all right? So that's why we can look at them separately. But since it's a LTI, we know that we can add these two together, these two responses. So now, let's say here, this is the equation that you will use when you had different input to your system. So you have RS, then you can always use this block for, so I'm going to call this TD T disturbance. And this is G, which is your plant. If you had process noise, it would show up here, right, in the feedback loop, N of S. And then this would be your H, right? Now, here, let's say like that. You have to find, for finding transfer function, you have to find your Y, your output. Your output is Y over, your transfer function is your output over input, right? Now, you don't have only one input, you have 3 inputs. So if we write the output in terms of input, I'm going to make this a small to create myself some room. This is OCD right there in flesh for you. So you have to do some block diagram reduction and some superposition here. I'm just going to write the final solution, but it will make sense when you see it. All right. Makes sense that you'll understand what happened. Your Y becomes GCG. So your controller block diagram, your controller transfer function times the plant transfer function, 1 plus GCG R plus GCG 1 plus GCG TD minus GCG 1 plus GCGN, right? Then when you're calculating error is input minus Y, that's output. So if you wanted to consider all of them together, that would be your output. Then your error would be your input minus all of them. But when we're saying that, hey, let's just consider the actual input, you say this is 0, this is 0, right? Then you say, let's see what's the impact of my disturbance, process noise. You say, let's say this is 0, this is 0. So you 0 the rest of them and use what's left for as a transfer function of your system. Okay, so if you follow this, then you don't have to, it would work for all of your system if you can rearrange them like that block diagram. Controller, your process noise usually shows up there, your plant and your sensor. Now, what if my block diagram was in front of my summing point? Well, we know how we can move the summing point, right? Create the block diagram so that it looks like this. Then you can follow this equation to find the output, and then the error is input minus output. Now, why is the error is important? Well, if we want to see if this is just rejecting a disturbance, we will say let's make everything 0 except for disturbance. That's your transfer function. You find the steady state error. That has to be 0, right? Same for measurement noise. If you want to see how much your sensor is impacting your system. Does that make sense now? Yes, kind of. So this is a very important equation to have. But in your homework, you have to actually show it to me. So we're going to do that in your homework. Don't think we have much time for this. What I'm going to do is you're going to read this and try to brainstorm how would you solve this problem. All right. And then I can just write down the solution and give it to you, or make you the class participation another time, or homework. Read this question, and then let's have a quick discussion. How would you approach this to solve it? Does this block diagram look familiar? Like, kind of like that? Okay, so we kind of are in the zone. Everyone is looking up. I don't know if you're reading it or you're daydreaming. It's Friday, I know. Yes. Okay, so what is this question is asking? By the way, this is just K, not K2, because we only have K and K1. What is this question asking? Like, what are you being asked to do? Like, let's understand that, and then we can all go home. So one of the Ks is your controller for your, so K1 is the inside loop, right? So there are two controllers here. This is a loop. So you could have like interloop controllers, right? So there is one inside, which is the K there is not the controller per se, it's kind of the effect of your feedback. And then you have a K that's your amplifier, is your controller, right? So you're being asked to define this value so you can meet some requirements. So one is the controller, one is how you're modeling your sensor basically, right? Now, first thing you do, you will make that interloop to go away. How do you do that? Just feedback and feedback, right? Reduce that. So you have a block of amplifier. This is your process, your plan. Now you have controller, plan, disturbance coming in. Now the question is asking that design these K values such that you have specific requirements. Now, the first requirement, what does the first requirement tell you? How does from person overshoot? Like answer that and then go home. What do you learn from that? So we know it could be second order above, right? But we have a transfer function already, so we know that. What else can you tell me from person overshoot? Because that's one of your requirements.
Like the location.
The what? So it is how much it goes up, right?
Yeah.
But what does it tell you in terms of system specification? Do you remember the equation of your overshoot? What's in there? Damping. So it is telling you your damping has to be some certain value. So it basically you are designing the controller, but also manipulating your process, right? Sometimes you can do that. So you are adjusting the damping of your system also when you're designing this controller or manipulating your system. So designing controllers or manipulating your system to achieve what you want is not just having a gain or a steady state error. It can expand to all those specifications you have. Damping is actually a very important aspect of a system that you can manipulate. All right, okay, I'll pick it up on Monday. All right, you have a class participation to do.